Hey everybody, I'd love to introduce Sherrie Wang from MIT, who's been looking at the Earth from space, focusing on crop analysis and just I think mostly a bit vegetative analysis of what's growing out there. Welcome, Sherrie.
Great, thanks a lot for having me. Yeah, so today I'll be talking about some of our lab's most recent work, and I'll start by giving an overview also of just generally what we do and give a few shorter examples before diving into the longer projects. And I'm happy to take questions as we go, or if there's a different format, I'm happy to follow that too.
Oh yeah, there are definitely questions in the middle. That'd be fantastic. Okay. Thank you.
Great, I'll just stop intermittently and ask for questions. So really a lot of the driving motivation behind what we do in the group is that we now have unprecedented observation of our planet. So here you can see on the left a graph of the number of Earth observation satellites launched per year for the last few decades. And you can see it's really increased a lot in the last decade, particularly commercial satellites, but also public ones as well. And you can see on the right, if you look at specific trends in satellites, so these are all multispectral sensors actually, the resolution is getting better spatially and temporally. So you've gone from something like Landsat, which is a very long-running constellation, has gone from 30-meter resolution with 8-day revisit to now we have Sentinel-2 from the European Space Agency at 10-meter resolution, 5-day revisit, and then commercial Planet satellites that are close to 4-meter resolution with pretty much daily revisit. And to give you maybe, I know not everyone probably works on Earth observation, so just to give you some intuition of kind of the things that we can see now. This is with Landsat as it goes back to the 80s, but you can see, for example, deforestation in Bolivia driven by agricultural expansion. And you can see many things like this. So we can see, we already saw an example both of agriculture and forests. You can also see economic activity from a different kind of sensor, sensing night lights. So this is imagery taken at night, whereas most of the time we're looking at images taken during the day. And then you can also see natural disasters like floods through both optical imagery, like the kind we're used to seeing when we take a picture, but also radar and other modalities. So I didn't mention the different modalities that exist, but there's not only multispectral or RGB imagery, but there's tons of different modalities now, and that has also increased greatly in the last couple decades. Of course, I think this part we're probably all more familiar with. In the last 10 years, we've also seen a dramatic improvement in our ability to analyze kind of unstructured data like images, thanks to, of course, the advent of deep learning. So you can see on the left, the number of papers published at the intersection of deep learning and remote sensing has really grown kind of exponentially. And you have now large-scale data sets, for example, Google Open Building Footprints, Global Renewables Watch from, I believe, Microsoft, and Global Forest Watch, all products of machine learning applied to satellite imagery at scale. So what I want to do in my group, which we call the Earth Intelligence Lab, is to bring us from where we currently are, which is a lot of variables, especially related to agriculture, but also many other things, which are sensed or collected via surveys in a very sparse way, where we only have data about usually only in high-income countries where we have good statistical infrastructure, and oftentimes only at national level, or maybe at best, one administrative level higher than that, or lower than that rather, to where we want to be, which is to be able to monitor the world, both spatially very detailed and also temporally very detailed. And then you don't want to have gaps in places around the world just because there's not kind of good statistical infrastructure on the ground, but you want to fill in those gaps using remote sensing. That's kind of the goal of our group. And there's many ways we can imagine getting there. I think we can divide the work that needs to be done into three main categories. One is developing algorithms to process all of that remote sensing data, especially in settings where labels are scarce. So a lot of our focus is developing machine learning algorithms that work in label scarce settings, or maybe can transfer knowledge that we have from high income regions to lower income regions. We want to often also leverage the unique characteristics of remote sensing data. Obviously, there's a ton of work done, especially now in the NLP domain or in kind of computer vision, but there are also unique attributes of remote sensing data, which, as I mentioned, come in a very diverse kind of set of modalities that we want to obviously be mindful of the physical properties of the data when we create algorithms for them. So not just, I mean, we do obviously borrow a lot of ideas from computer vision, but it's not enough just to do only that. We also create benchmarks for the machine learning community so that they can test their new algorithms not only on, maybe canonical, say, vision data sets, but also on remote sensing data sets. And a lot of these data sets obviously have a lot of kind of global social importance. So that's the algorithms box. Once we have algorithms, or honestly, a lot of times, even just with fairly simple algorithms, you can already develop large-scale data products. So I mentioned global forest watch. That is, I think, the output of or it used to be at least, the output of a decision tree-based algorithm rather than, fancy deep learning. So it's possible to already make a lot of progress making data products, not necessarily with super fancy algorithms, but what we do care about, of course, is always accuracy, and also for many applications, valid uncertainty quantification, because we then want to use those data products for downstream analyses like causal inference. In our case, in my group, we're really interested in, again, the promise that remote sensing has to fill in data gaps in places around the world, often low income, without good ground data. And then in order to create data products, we often also explore the use of novel data sources. So, kind of sources that maybe a particular remote sensing modality wasn't developed in order to do, but we test, a modality, for example, like LiDAR, to see if it can be used to map crops, even if it was only originally developed to map forests. And then once we have data products, we're interested in using them to assess the impact of policies, maybe for agriculture management practices by the farmers, new technologies, and of course, extreme weather events and climate change. All right, so that's kind of the overview of our kind of group. And to give a few examples that I won't get into in detail, although I'm happy to answer any questions about these. Here, I'm going to give a couple of examples of algorithmic works that we've done, as well as data product development, and then downstream inference. So in the algorithmic category, I would say, here's an example. Now, I guess I can't believe this paper was from, 7 years ago now, but this is a fairly early example of doing representation learning on satellite imagery, again, making use of kind of the unique properties of satellite imagery. And this algorithm we call tile to vec, and the idea was that generally speaking, things that are close together on the Earth's surface should be more similar to each other, and things that are farther apart geographically should be different from each other, more different from each other. And so the algorithm is very simple. You just sample these triplets where two of the tiles are close to each other. So there's an anchor tile and the neighbor tile. They're sampled within some radius of each other. And then there's a distant tile, which is outside of that radius. And then we just have a triplet loss that tries to bring together the representation of the anchor and the neighbor, and then push apart the representations of the anchor and the distant tile. And just by this triplet loss, we trained this on about, I think, 500,000 tiles in California on pretty high resolution aerial imagery. And we were able to show that the features that we learned through this algorithm, TilePivec, are able to outperform an end-to-end supervised machine learning or deep learning architecture. So we tried a few different ones. You can see here ResNet, Inception, DenseNet at the time. Those were some of the state-of-the-art ones. And we found that, up to having 50,000 labeled examples, TilePivec features are actually able to outperform end-to-end supervised learning this was a crop type / very high resolution or high kind of granularity land cover classification task. Okay, another more recent work now, when LLMs and these vision language models started coming out in the last few years, we wondered, do we need to develop kind of geospatial foundation models, or can these VLMs just perform a lot of the tasks that we're already interested in? So we created a pretty comprehensive set of tasks, a benchmark basically, and we evaluated GPT-4 vision and then other state-of-the-art models, including open source ones at the time, on these tasks. Of course, these VLMs, they can't do everything. Like they don't output like a segmentation mask, or at the time they didn't. But we chose tasks that they could answer. So it's a lot of Q&A or multiple choice kind of tasks in order to gauge whether they're able to do any of these tasks. And so what we found was that, they actually are quite impressive at generating captions for images. And they also can recognize landmarks from high resolution satellite or aerial images. A lot of times they might use OCR, or they can just recognize the way that buildings look. So for example, they could recognize that Boston City Hall has a particular style of architecture. So it is able to tap into the vast world knowledge that these models have from the entire internet, and yeah, recognize a lot of landmarks. But what we found was that they're not good at counting, and they're not good at localization. So for example, if you ask this is GPT-4V to localize the stadium in the image, it's not able to generate a bounding box that's actually very accurate. So the IOU on that task was quite low. Okay, so obviously that was a couple generations ago of models. So we're also updating this benchmark and seeing if some of the weaknesses are going away now with the more recent model releases. Okay, cool. So I'll talk about, I don't know if there are any questions about those specific projects. I'm happy to take any. Okay, so one thing I just wanted to mention is that we've recently kind of ventured into weather forecasting, especially at very, very local scales. So we currently have an ongoing project using kind of the high resolution satellite data that I talked about to see if we can interpolate weather at very high resolution. This project is a little bit different. So this project, we looked at if we can combine gridded weather forecasts. So that would be I don't know if folks in the audience are familiar with weather data sets, but a data set like IFS from ECMWF, or HRR in the US has a forecast as well. So there's global and regional forecasts. And what we notice is that the forecasts often don't match surface variables very well. And that's especially true for wind, which you can see in the scatter plot in the top right. So the surface winds are generally over land, way over predicted in terms of magnitude. And that's because surface friction is not adequately modeled in the physical models that generate these forecasts. So you can see for temperature, it's quite a bit better in terms of the correlation between the observed, which is on the x-axis, and the predicted, or in this case, it's actually a reanalysis product on the y-axis. So even when data is assimilated into these forecasts, there's still a lot of mismatch at the surface. Dew point is kind of in between wind and temperature. So we noticed the discrepancy, and we wondered if we could generate better forecasts in the case where you have historical data at a particular location on the ground. So the way we did this was we had a transformer that basically could ingest this multimodal data. One was a very coarsely gridded forecast. In this case, we were working in the northeast of the US, so we used the HRR product. And then the other modality that we took in was weather station data from nearby weather stations on the ground. And then the task was to forecast at this specific station that you're at. So you know this station's historical data, you know your neighboring station's recent measurements, and then you also know what the forecast is kind of from this regional or especially global weather, numerical weather model. And it turns out if you combine these data sets, you can reduce the amount of error in your forecast relative to the regional or global weather forecast by, in the case of wind, you can reduce the error by 80%. So having that local context kind of implicit in the historical data of a particular weather station allows you to reduce the error a great deal. And that's something you can see in the leftmost plot, which is the green line. The transformer was the best model that we tried. We tried a bunch of other architectures as well. And then the global model, the regional US models forecast is a much higher error. All right, so this was published last year in James.
So this is a rather interesting idea because you're using, I think, high resolution static features with low resolution dynamic features, right?
Oh, in this particular case, we're using also high resolution dynamic features because we have the time series, the historical time series, like from the last, say, 24 hours of a particular weather station.
Okay. So you incorporate weather station, specifically raw data from weather stations.
Yes.
Okay.
To forecast
Then,
to forecast that weather station's future observations.
Right, and then you kind of simulate what the reanalysis would have done. I mean, that's what HRR essentially would do, like a kind of a reanalysis kind of thing for the future.
Yes, I think we ran a bunch of different model specs. One was using HRR reanalysis as like the future forecast, but actually in the paper we also show results for if you're using the HRR forecast. So at a particular time stamp, we would give the model, let's say we would give the model for a particular weather station its historical weather observations for the last, let's say, 24 hours, neighboring weather station observations for the last 24 hours, HRR reanalysis for the last 24 hours, and then HRR forecast out to some lead time that we are trying to forecast to. And we're trying to predict the observed the observations at this weather station in the future in up to some lead hours.
Okay, but not satellite imagery.
No, in this case, actually, no, not satellite imagery. We have ongoing work that I don't have in this deck, but we have ongoing work where we do incorporate satellite imagery. So that's the direction that this work is going. Because we can only apply this model at locations where we have some historical weather observations. But if we want to fill in, if we want to interpolate between those weather stations, or if we want to have predictions everywhere, then we need some other data source. And in that case, we can bring in something like relatively static satellite data.
Right, and you're focusing on things like roughness. So if you had a data product on surface roughness, that would be a pretty obvious data layer.
Yeah, exactly.
Okay, awesome. Thank you.
Yep. So that's what we're working on right now. And yeah, hopefully I can release and talk about those results soon. Okay, so in terms of data products, back to agriculture, here's an example where this is a project, like a line of work that I started in my PhD. The idea is that, so I'll talk about this in the longer project as well, but we don't have crop type maps globally of what people are growing where, for even the major cereals in the world. So one observation we had was that crops like maize and sugarcane are taller than pretty much any other annual crop that's grown. So much taller than soybeans and rice, wheat. And we now have LiDAR from space from a sensor called JEDI, which is on the International Space Station. And that sensor was created to map forest height. But we wondered whether it would also be able to tell tall crops like sugarcane and maize from shorter crops like soybeans. So we found in a first paper that, yes, actually you could do that. So then in this particular paper, we used that algorithm that we developed to map sugarcane globally using this height difference between sugarcane and other crops. And in the case of sugarcane, it also has a much longer growing season than most of these other kind of staple crops. So that was another differentiator that allowed us to figure out where sugarcane is versus potentially other tall crops like maize, which have a much shorter growing season. So here's an example of going from kind of an insight that we had about what sensors are available and the properties of crops to actually a global, in this case, data product for sugarcane. Okay, and then maybe I'll just talk really
Actually,
quickly.
question.
Yeah.
The whole idea, I mean, using LiDAR is fantastic, but JEDI is an unusually tricky one because it has like these, like it's highly spotty because of like overflight things, especially over the equator.
Yes.
How do you have to, what do you have to do to recover that, to use this global analysis?
Yeah, so we used JEDI to figure out where the crops are tall, but then we can't use it to create the kind of wall-to-wall, like gapless map, right? So what we did was we then use the JEDI as labels for here's a tall crop, and then we combine the tallness with, in the case of sugarcane, a long growing season, and then those become locally, for example, in Brazil or in Thailand, those points where JEDI does have an overpass, we would say we're pretty sure that's sugarcane. So that's our sugarcane label for Brazil or Thailand or whatever country we're in. And then we use Sentinel-2, which is this gapless satellite, to then create a Sentinel-2 based model to predict the JEDI labels. And that Sentinel-2 map is what we're showing here, ultimately.
Got it. Thank you.
Yeah, so we have local models in each country because Sentinel-2 features, or at least at the time it was thought that Sentinel-2 features, you can't just train them in Brazil and expect that to work in Thailand.
Right.
So we use JEDI to generate these local labels so that we can create local models that then work in each country.
Cool. So yeah, a question here. How well did it work? Like, how did you validate? Yeah.
Oh yeah.
So how did you validate this?
We did our best to validate. I mean, there's not ground data in every single country about sugarcane, but we validated against other sugarcane maps if they're kind of often, they may be available in a subset of these locations. Other research teams may have created them for a particular year. Usually they're kind of one-off research projects, or in some cases, in the US, for example, there's we have a cropland data layer we can compare to that particular product. or there may just be, you know, kind of scattered research data sets. I think in India, we had some data from a partnership with a company that makes an app called Plantix, where they have collected some data from farmers, and it was, you know, anonymized data that we were able to check against. So it was kind of, we just did our best to grab whatever data that was either public or through collaborations that we were able to use for validation. But it's definitely, you know, if we had ground data everywhere, obviously we would just be using that ground data to train models. So yeah.
Makes sense. And Rahul, you had a
I have one
question?
question. Yeah. The question, like, our India has the shape file is totally different by where I saw in the picture. Like, we are completely the part of the Jammu and Kashmir, but here it's not showing. It's like globally the taking of shape file, like our Indian shape file is totally different from the here the shape file.
Wait, sorry, I don't think I understood the question.
So I think, yeah, that he has a different shapefile for India. So maybe that's a good thing offline for who you can send Sherrie an email with, like,
Oh,
the kind
I
of
see.
data you have that's different from these predictions.
Like our Indian shape file has to be modified right now in 2022, and they're part of the Jammu and Kashmir. Here is not showing the Jammu and Kashmir of shape file. That is like the older one that you are using here.
Okay, so we use a data set called
You can use the dataset WIRS India. Here you can get the shape file of the official shape file of India.
I understand. We got all our shape files from the same source. But yeah, I guess it's good to know for the future. We'll get a more up to date one.
Thank you.
Okay, thank you. Okay, so I talked about a few examples of algorithms and then an example of a data product. In terms of downstream inference, here's an example where we predicted using remote sensing data what the Clean Water Act in the US regulates. And so we were able to train a satellite, or actually it was an aerial image plus a bunch of other geospatial layers as inputs, a CNN on a stack of geospatial data to predict the Army Corps of Engineers rulings about whether a particular wetland or stream was regulated by the Clean Water Act or not. So the Clean Water Act, just for a bit of background, is the major kind of federal law in the US that says, you know, you can't pollute in major kind of waters. You can't fill in certain types of water bodies to be dry land, to develop real estate and so on. So we wanted to know, you know, under different administrations, because different administrations kind of have different ways of implementing the Clean Water Act, exactly what is considered regulated and therefore cannot be polluted and cannot be developed versus, you know, under a different administration, did things become deregulated? So the long story short is that, you know, this model achieved reasonable accuracy on predicting human-made decisions about whether a water body is regulated or not. And then we applied it to the US at continent, or like at CONUS scale. And then we found that under, basically on the right, this is under the first Trump administration, there was massive deregulation of both streams and wetlands. And this was something that was not explicitly spelled out before. It was always speculated how much might have been deregulated, but this is the first time that it was mapped explicitly. And this is something that the EPA was quite excited about. Okay, so I'm going to skip over this one and just get into our first more in-depth project. So this project, as I mentioned already, for the sugarcane work, we are trying to create crop type maps in places around the world where we don't have good statistical infrastructure that even tells us, you know, how much of a particular crop is grown at a national level or subnational level or district level. And the problem, as I mentioned, is so we don't have these maps everywhere in the world. This is a map from a few years ago showing where we have complete maps, where we have incomplete maps, and where we have no maps at all. And you can see, obviously, in Africa, there's very few countries, or basically just South Africa has crop type maps. And then also, in Latin America and in South and Southeast Asia, the maps are often only for a very small number of crops and often quite coarse resolution. And the typical recipe for creating a crop type map is you have a satellite time series and use some kind of machine learning algorithm, random forest, or some kind of neural network now are the most common ones. And then you predict these ground labels that you have about crop type. And the ground labels is really like the bottleneck for creating these maps, because again, as I mentioned, it's like kind of a catch-22. If you had statistical infrastructure to have all these field surveys of what farmers are growing where, then you could just aggregate that to get your county level cropped area or production statistics. And you would also have that data to train a machine learning model. But when you don't have that, then it's you have neither your aggregate statistics nor the ability to train such a model. So our question in this paper was, is it possible to find remote sensing features that are invariant to geographic shift? And the conventional wisdom that we're challenging is that in order to create a crop type map in a particular country or in a particular region, you need ground labels in that region in order to map crops. And that's because, crops, here, maybe I'll skip to this slide. So crops are differentiated from each other based on their phenological and spectral differences. So phenological means like the timing of when they grow, when they get harvested, like how long their growing season is and when they get harvested, as well as the way that the plants look under like different wavelengths of reflectance, basically, that we can measure in satellite time series. So it's the temporal information in combination with the spectral information that allows us to distinguish crop types from each other. And in different regions, the timing of the growing season is shifting. And then sometimes the exact variety of the crop, is changing as well. And then climatic conditions are different, soils can be different. So there's enough differences that so far it has not really been possible to, say, train a model to classify corn versus soybeans in the US and then just expect it to immediately do well in Brazil. So we just haven't had a model like that. But what we are trying to accomplish in this paper is to see, can we identify features where, instead of having to create 4 different models, if you wanted to map crop types in these 4 different countries, can you then imagine a model that can be trained in, for example, places like Brazil or Poland, where you have some data, and then apply them in places like Mali and Angola, where you don't have any data, or like very little data or very spotty data. So in terms of how we might engineer these features, our original thought was maybe hyperspectral imagery can allow us to identify fingerprints of certain crop types. And hyperspectral imagery is available more so now than ever before. But what we actually found was that if you do a 2-dimensional convolution in the spectral temporal space, that learns, I would say, surprisingly invariant features. So that would be this last kind of way of extracting features shown here. The other 2 ways of extracting features are kind of very common ones in the literature. So one is, you summarize a time series of satellite acquisitions by running something like a harmonic regression. That way, you're not bothered by different acquisition dates by the satellite, or, sometimes you might have a gap of a couple weeks or even longer sometimes. So you kind of let the regression summarize the characteristics of the time series, and then you use the coefficients of that regression, usually in a random forest or SVM, to classify crop types. And then another very common way that people classify crops is you do a 1D convolution just across the time series dimension, so not also across the spectral dimension. These are 2 of the very common ways. You can also people also just kind of bin the days of the year into groups, and then they might just run like a MLP on that feature vector. Nowadays, we also see more and more transformer-based architectures. I think the issue with that is a lot of times they're more data hungry, and we don't often have a ton of ground labels. So there are people who have created lightweight transformers as well that seem to work quite well, and that's on our to-do list as a comparison. But I guess in order to test whether our model is able to transfer well, we first had to compile a data set that's global that allows us to do a bunch of different kinds of transfer learning experiments. So we compiled this data set that we call crop globe, and you can see it covers many different crops in the US. Then we have soybeans in Argentina. We have mostly corn and soybeans, and also some wheat and rice in France. We have some data from the UK. We have rice from China, and then we have some sugarcane, cotton, and then other classes in Australia. Okay, so this data set in total, we compiled over 300,000 samples, and then we are using Sentinel-2 time series data for 2023. As I mentioned, we originally thought maybe hyperspectral data would allow us to do this transfer. So I'm not showing it here, but we also, for a subset of these 300,000 samples, we were able to get hyperspectral data from NASA's EMIT satellite or sensor, which is also on the ISS. Okay, so as I mentioned, this kind of 2D convolution in the joint spectral temporal space is eventually, and you'll see that in the next slide, the architecture that allowed us to learn surprisingly invariant features for crop type mapping, which has not been documented before. So CropNet is actually, as I mentioned, there's not, for many places around the world, there's not a ton of data for training a machine learning model or deep learning model. So we kept CropNet fairly lightweight. In this case, I think it still has over 2 million parameters, even as a lightweight 9-layer CNN. Another feature of CropNet, so it's pretty simple, it's just a convolutional neural network, but it has some spatial dropout where we occasionally drop out entire channels in order to encourage more robust representation learning. Okay, we also performed extensive data augmentation where we did time shifts because, as I mentioned, the exact phenology when the crop grows and when it senesces and when it's harvested allows us to distinguish crops from each other in a particular region. But if we go to a different region, the exact timing might change. So we tried time shift, time scale, and then magnitude warping, with the assumption that all of these transformations would still retain kind of the crop type label. And indeed, we find that all of these transformations do help learn a more robust and transferable model. All right, so here's the big table, excuse me, of results where we do a bunch of cross-region transfer experiments. So the first set of rows, we show results for training on one country and testing on a completely different country. Then the second set of rows is training on a country on one continent and then going to a completely different continent. And then the last one is cross-hemisphere. So in this case, training in the northern hemisphere and then testing on a country in the southern hemisphere, where the growing season is way more different. So we have a bunch of methods here. We have what I mentioned was the harmonic regression way of extracting features combined with a random forest. Random forest combined with this 1D median feature extraction method. Then we have CropNet combined with different types of features. The 2D median is the one that I talked about where you're doing a 2D convolution in the joint spectral temporal space. And then with aug-M after that is the version of the model trained on also augmented data. And the kind of numbers at the bottom here with a plus sign on each row is how much the augmentation helped above the previous row. Okay, so what you'll notice is that the kind of standard way of doing things, which is either the random forest harmonic or median 1D features, sometimes they do work reasonably well. If you go from training a model in France and then applying it in Belgium, you're not doing too bad when you use CropNet with a 1D median features. But when you do this across continent, you're seeing pretty bad performance for those types of features. And that's true for cross hemisphere as well, for the most part. So for example, if you train on the US and you apply the model to do crop type mapping in France, if you don't use these 2D features, the best model that you get overall accuracy wise is like 67%. Versus if you then switch to this 2D convolution over the joint spectral temporal space, you gain 20% accuracy, 20% F1, which is a lot. So you can see basically across the board, the best model is the last one, which is using 2D features, 2D convolutional features with pretty heavy time series data augmentation. And data augmentation doesn't always help that much. You can see some of these numbers are like less than 1%. But then we do find in certain cases, like when we are transferring a model from France to the US or from France to Argentina, that augmentation can actually help significantly. I think there's a question in the chat.
Let's see, this is, what do you think the reason could be for the performance difference varying spatially?
Oh yeah, so different countries also have different numbers of crops that we're trying to distinguish from each other. Argentina, for example, we're only trying to differentiate soybeans from non-soybeans. So that's like a binary classification. So that's a relatively easier case than US has more crop types and France has more crop types, for example. So that's one. It could also be that in certain countries, the timing of the crops are more similar to each other than others. Yeah, I think also in general, when the yields are lower, we expect the crop type mapping task to be harder because the signal to noise ratio is just lower in general.
Oh, thank you. A follow-up question: Do you think this data gets affected by how many different types of crops are present, or how many different types of vegetations are present at the same time? Like if they're growing two simultaneous crops, perhaps.
Oh, you mean in one field if they're doing intercropping?
Mm-hmm.
Yes, I think an intercropping would definitely be a more challenging case, and that's very common in Africa. So that's kind of one of the next things we want to tackle is applying this model to Africa, where the yields are biomass is much lower, and also we have much more intercropping. I think we would probably start by seeing if we can recover the kind of taller crop in the intercropping situation, which would usually be maize. Yeah, it seems like it could be quite hard to unmix the two crops.
Thank you.
But yeah, in these countries, we don't run into intercropping really much at all.
So another question, this maybe is for the whole field. I mean, I noticed you doing something that's for crops, but in a way that does not care that they are in fact crops. So this could be about your buildings. Is there a way of incorporating like crops, like knowing that these are in fact crops with specific plant phenology, they're annual plants, not perennials like forests and so on? In what ways can you bias it by knowing that they're crops?
Oh, I guess one thing, so I didn't go into the weeds of this, but we do make a choice about kind of which general months we give the model. So there are some bias or some domain knowledge there where we know the growing season in Argentina is, a bit different from the growing season in the US, or Australia is a bit different from the US, or I guess quite different from the US in terms of absolute months. So we do use that information to kind of have a starting point for which months the model should be looking at in terms of like what time series the model gets fed. And then I don't know if that.
Yeah, that helps. And there's also a bunch of other data sets like SPAM, the ones that use administrative data on crop yields. And it's available globally at a course resolution. Are these kind of different modalities relevant?
I think for SPAM, we can once, if we create a data product, compare against it. And I think we can also use these data products to kind of guide the timing that we're looking at, as well as, I mean, we have work previously that showed that if you have something like an aggregate level statistics that you trust, it's possible to use that data to improve transfer from one region to another. So yeah, so like in the US, let's say it's 50-50 corn and soybean in the Midwest. But you know, in Argentina, I don't actually know what the mix is, but let's say it's not 50-50. But you can use the information you have about Argentina's soy versus other crop mix to move the decision boundary from, you know, a US based model. But I think in that case we were working with like a linear decision boundaries that we could shift quite easily, like pretty basic models like LDA. So in terms of deep learning, I think we would have to, I mean, I don't know, we may try retraining a model with different sample weights, for example, and see if that helps transfer. But in this case, the nice thing about this model is that we didn't have to take any of that into account. We just trained it on the distribution in a particular country and then applied it to the distribution as is in another country, and we're already seeing, you know, quite high performance. So it seems like the model is picking up on some fingerprints of crops in this combined spectral temporal dimension, which, you know, honestly, I was very surprised by these results. I kind of had set out to show that Sentinel-2 features are the baseline, they don't work, and then, you know, hyperspectral features transfer. Like that was kind of like my hypothesis. And then the fact that this worked with data augmentation and with these 2D features was, yeah, I think it was new. Just nobody knew that was possible.
Well, interesting. And Brooke, you had a question?
Yeah, just to quickly jump in. Hi, Sherrie. Thanks for sharing. It's super interesting.
Yeah.
I wonder, so it seems to be picking up some like geographic and covariate shifts here. I wonder if you take this like best performing CropNet here and compare it to like a off-the-shelf vanilla, I don't know, unit on an embedding level. Can we pick up some like feature salient, resilient features, like pattern that can point us in the direction of which features are resilient to distribution shifts, if that makes any sense.
I guess what we did, maybe this is kind of in the direction of kind of opening the black box. So we looked at the feature importance in the spectral temporal domain. And the way that we did this meant that, you know, it was kind of model specific, and then it was specific to the data set that we were testing or transferring the model to. So what you can see is that for soybeans in the top row, the timing can be really different for different regions. Like Argentina, you can see, you know, for the shortwave infrared bands, it's kind of the most important features are occurring, you know, at the end of the year, or kind of like, you know, December 31st or so, versus in the US, those features are lighting up in October, versus in France, they're lighting up in June. However, the specific bands that are lighting up, there's some consistency between the different regions, and same thing with rice. So that to us suggests that, you know, it's a 2D kernel that we're learning. So there's something about that the kernel, there's like some spectral temporal pattern that's appearing, and it can appear in different times of year. But if it matches that pattern, then it looks like soybeans or it looks like rice. Does that make sense? And is
Oh, yeah,
that
this is,
hopefully that's related? Yeah.
oh yeah, very, very intriguing. Thank you for sharing.
Okay. This is just to show that we also compared to other architectures. Oh, okay. Sorry. I mentioned that CropNet still has millions of parameters. In this case, that was actually 4.7. I think a more recent version was a bit smaller, but anyway, you can see that the other models that we tried have more parameters, and in all these cases, they also often do okay, although not always. You can see sometimes they're quite a bit worse than CropNet, but CropNet is always, at least, except for, I guess, this one row. It's pretty much always at least a bit better. So I think, in this case, a pretty small model works just fine for this task, and we may not be learning very, very complex, spectral temporal features. So a small model's doing well. Okay, we also tried tuning the temporal window and time span, and this is basically just showing that, well, first of all, you can see that cross-country transfer is always easier and resulting in higher performance than transferring farther away. But yeah, basically this is just to show that we did tune, what is the temporal window that we should kind of aggregate satellite time series over, and then also tuning the duration of when we train and apply these models. So I think we found that for cross-continent and cross-hemisphere transfers, it was generally a little bit better to not just give the model the whole year's data, although if you do, it's still performing pretty well. Okay. And this is just to show examples of average time series for some of the major crops that we're trying to distinguish from each other. We showed France and the US partly because in the results table, the transfer from France to the US was actually the single lowest or kind of most difficult case. And we partly just wanted to understand why and see if maybe if we could visualize the time series, we could have a hypothesis to why it was more difficult. Something that we noticed is that in France, NDVI values are already high in the early part of the year from January to April. So there's more vegetation already on the ground in that early part of the year. It could be winter crops, or it could be crop rotation or cover crops, which are, I guess, more likely to exist in France than in the US. And that may be, yeah, that may make it harder to transfer from France to the US when those conditions are different and we maybe don't truncate that part of the year. So, okay, I think with that, since we're at time, I'll just conclude and say that, we're still adding comparisons to some of the transformer-based architectures, as well as kind of foundation model embeddings like Alpha Earth to see how they transfer, although I would say it's been documented already in the literature that it seems like foundation model features don't necessarily transfer well geographically. And then, yeah, we're very excited about evaluating the performance, not only on the regions where we have data and can develop the method, but also in, of course, places where we don't have any crop type maps and also have very sparse crop surveys or statistics, like in Africa and throughout Asia. So here's a QR code for the paper, and yeah, it's available on arXiv if you're interested in reading more about it. So
Well, yeah, thank you very much.
Questions?
Well, yeah. So let me ask you one thing. Like the way you described this, it seems like the big insight was less so that less fancy architecture. It was really more that you found the right features kind of from more background knowledge. So that, of course, makes me think, how do you automate this? And with the rise of LLMs, it seems like, yeah, you can read a bunch of these articles to suggest kind of the ideas that you kind of with your brains figured out. So to what extent can you think of, inspiration that can create the next version of this with smarter, more refined domain-specific features?
That's a good question. Yeah, I guess, yeah, LLMs would be a great tool to synthesize kind of what we know from all sorts of different modalities, because it's relatively rare for a particular researcher to be an expert in every single remote sensing modality. But yeah, it's true that one way that we could automate this more, or just iterate faster on these ideas of identifying more invariant features, would be to use these tools to kind of synthesize the literature from different domains, maybe remote sensing domains that one might not be super familiar with, and propose ideas for things that might be invariant for different applications. I think that's an interesting idea. Yeah.
Nice. And Nibod, last question.
Oh, thank you for the talk. Could you revisit your slide on showing the reanalysis results for different architectures for the local weather?
Oh, for local weather. Yes.
Oh, yeah. So I'm curious how come the because usually in these in applications for climate data or weather in this case, the attention mechanism usually has the least performance advantages. So do you have any thoughts on how come the transformer based model seems to have the best performance here?
Yeah, this is something we talked about in the team. I mean, I guess our hypothesis is it's able to figure out which of its neighbors it should look at, as well as which modality is more important for a particular station, conditional on its historical observations and the relationship between its historical observations and its neighboring stations' observations, as well as the global weather product and So I think, given that there's cross attention between the different modalities, and then also between different weather stations, it seems like that mechanism allowed it to figure out what's the most useful for a particular prediction.
In particular, because you also have the GNN results, and it seems like those don't do so well. So it almost seems like the for the data that you have, it's like it could be represented like complete graph in some sense, because the GNN doesn't seem to be doing so well.
Yeah, we talked about this as well. I'm trying to remember what the conclusion was. We tried a bunch of different graph architectures, or like graph connectivity. We did nearest neighbor. We did like a Delaunay triangulation.
Oh.
And then we did a complete graph, and then I don't think they differed that much from each other, actually. So yeah, but I think it's a good question. Why didn't the graph perform better? And in this case, it doesn't even perform better than the MLP. Yeah, I don't remember right now exactly what our conclusion was, but yeah, it's a good question.
Thank you.
Nice. Actually, this makes me think that you can just toss this analysis at Purple Air, and you'll get probably really excellent results. Because it seems to overcome all.
Yeah, that's actually something that one of my students is working on.
Oh, makes a lot of sense. Cool.
Yeah.
And Jandra, you had a question?
Yeah, one small theoretical question. Can we also detect the spread of disease in the different crops? Maybe it is in the short region.
Wait, sorry, the what? Can we detect?
Can we map the change in the crops because of the disease? And and we can constrain that because we know in the map.
Yes, so disease mapping is more challenging than crop type mapping because the changes are more subtle. You're talking about generally, well, it depends on the disease too, but generally leaves turning yellow and biomass being lower and, you know, brown, yellow, kind of looking for these kinds of colors. I think, or my personal hypothesis is that hyperspectral is probably a bit more promising for disease detection, especially if you're trying to figure out a specific disease. But I think it is probably possible, I think, to moderate to low accuracies with the kind of multispectral data that we're working with. Yeah, just because I think a lot of things can cause crops to look yellowish. And I think you need probably much higher spectral resolution to tell if it's, you know, if it's just water stressed. I mean, you can add other features too, like precipitation, and see, like, to maybe rule out water stress. But I think, yeah, I think
Yeah.
it would be relatively challenging. I think you'd have to kind of rule out other causes of plants looking yellow in order to
Yes.
conclude that it's like a disease. Or you can try to sense in a very high spectral resolution, and that may allow you to, that might yield a different pattern from different other kinds of crop stress.
Would forests be easier or harder? Because they're perennial, you have more time, but
For
more
disease?
things can happen. Yeah.
Not sure I have a initial reaction to that. I mean, I know tree species is hard. It's a hard
Mhm.
map. Yeah, in terms of disease, I guess, yeah, one thing we were looking at recently was kind of tree crop diseases, but we were still in very, very early stages of looking at that data. Yeah, I mean, it certainly, if it's a disease, it seems like it would just start looking bad and then just get worse over time in general. So
Right. You get more time that way. Yeah.
at some point, if it's gone downhill for long enough, maybe you can conclude with a very high accuracy that it's got a disease. But, you know, whether that's early enough to be useful, I guess maybe is the question.
Would the fact that they spread in frontiers be usable?
Sorry?
Tree, like a forest disease, they've spread on a frontier of some sort. Would that be a usable feature?
A frontier? Sorry, I don't think I.
Oh, so it comes from some place and starts walking through the forest because it's like touch kind of propagation.
Yeah, I think that if you were modeling a region as a whole, rather than taking a very, you know, local, either pixel level or tile level view of things, then yeah, with the temporal history, I think it seems like it would be possible. But then I think when you build a model like that, I guess my question would be, would that generalize to a different region if you train a model in a region where you have this kind of data that you're able to model the whole region? So I don't know, there's trade-offs. If you could do it at a tile level or pixel level, that would be powerful. Obviously, you could just apply that, you know, globally. But yeah, that may be harder than if you had some spatial temporal context.
That makes a lot of sense. Well, then, thank you very much. Thank you for sharing with us.
Yeah.
Thank you very much.
Great.
Have a good rest of the day.
All right. Thanks. Okay, bye.